right, so guys, here's sort of the big picture overview of what we're up to. So this is kind of amazing. We are starting the first to last unit of the year. They would call that in the cycling community the penultimate unit, which means the biggie before the end of the race. And really it is, guys. This is the stuff that you can guarantee yourself you will see on the test. The only thing now that they are guaranteeing us is that there will be a question. It could be a lab question, but there will be a question in free response on the test out of chapter 16 and 17 in our book. Guys, you are going to see this on the test. So here's the way we're going to approach this. Guys, this is going to be very, very reflexive. I don't know where it went. Lawson put it away somewhere. I actually sat down and mapped out the rest of the year. And guys, let me just show you. This is what the rest of the year literally looks like. So this is this unit. You'll notice that it's 9 class periods long. We are going to talk fundamentals of acids and bases today. We're going to talk about weak acids and bases next time, and we're going to bring icebox calculations back into the conversation as they apply to weak acids and bases. Then, guys, we're going to talk about the pHs of salt solutions. Who knew? It turns out that salt solutions also have pHs other than 7. Then, guys, we're going to talk about, on another day, what makes an acid, a base, and a alcohol, an alcohol. And we'll talk about that here. Then, guys, this gets nutty. Starting on that 5th day when we get into chapter 17, we are going to talk about what is called the common ion effect and buffers. And guys, I'll tell you stories later. This is the first time I ever remember being confused in my entire academic career. This is where chemistry fell apart for me in high school, and it wasn't my teacher's fault. I'll tell you about it later. But anyway, this is where this gets a little nutty. But the thing that's nice is because I struggled here, I've also invested a lot of time in getting good at teaching it. So it'll be a good day, but it's deep material. Then, guys, we're going to start talking about what we do with buffers, titrating them. Then, guys, we'll talk on a 7th day about strong acid-base titrations. And then we're also going to throw in KSP really quickly. It doesn't really fit with titrations, but it's 2 short topics that we can lump together. Then, guys, we're going to talk about titrating weak acids and bases, and then it'll be the test. Now, the big deal is this. I've got some landmarks in our calendar that I'm keeping track of. One of those landmarks is here this unit and then the last unit. Guys, the landmark that I'm looking out for is spring break. So the first week of April is spring break. My goal here is to have this unit done and electrochemistry done and have introduced to you what we're going to be doing for the AP test review all before spring break. So as I'm keeping that in mind, guys, understand this. Let me go back here. So here again is the unit. But guys, this unit is not going to be completed in 9 class periods. This is going to be very reflexive. There are going to be times where I say, hey, let's slow down. We need more time here. There are going to be times when I say, let's speed this up because it's not worth spending the time here. Frankly, there are going to be times when I'm going to say, we're going to skip over this, read it at home, and let me know if you have questions. But guys, what we're trying to do is get everything done before spring break. And I know that's 2 months away, but it's going to get here like this, so we're going to be careful. So anyway, today what we're going to do is we're going to introduce acids and bases. So what you need to do is grab your equation sheet and flip this to the equilibria, so the page 12 side. Guys, you'll notice that this is not titled acids and bases. It's titled equilibria. The reason is because acids and bases, except for the strong acids and bases, all reach equilibria, and we really don't need equations to describe what the strong acids and bases do. So all the equations we're going to use represent the weak interactions that exist within weak acids and bases. So have that at hand, and let me go here, and let me grab this. And guys, we're going to cover a lot of material today. I doubt we're going to get done today, which is totally fine. It means that you'll pare your homework back as we go. But guys, what you're going to find is this. A lot of this is going to sort of ring in your ear as we go over this material, because a lot of what we're going to do is a review from last year. And guys, understand, we only spent one day on acids and bases last year. Do you remember what we talked about? Conjugate acids and bases, pH, amphoteric substances. Do you remember that? Well, what is amphoteric? It goes acid or base depending on what it's with. Guys, all of that stuff is going to come up today. But in addition to that, we're going to add some more understanding, some more base work, if you will, that will allow us to better understand this. So guys, we're going to scan through this where it's appropriate. We're going to slow down where it's needed. And we're going to start by talking about the Arrhenius definition for acids and bases. So guys, when we talk about the Arrhenius definition for acids and bases, it goes like this. An acid, by the Arrhenius definition, is a substance that increases the concentration of hydronia or hydrogen ion when dissolved in water. Now guys, understand that's true, but it's too limiting. And we'll talk about that in a minute. Every year I think about just skipping the Arrhenius definition for acids and bases, and I always hesitate to. But understand, guys, we are not going to think about acids as Arrhenius acids, frankly, because the definition is too tight. But I don't want to remove it from you, because sometimes it's a more simplified way of thinking about acids and bases. And I know that you don't understand the distinction now, but it'll become more apparent as we get into this more deeply. So then, guys, the definition of a base in the Arrhenius way of thinking is a substance that increases the hydroxide ion concentration when dissolved in water. Now guys, notice the two things that denote acids and bases. One is the type of ion that they increase, and then the other is that they're defined as being active in water. Those are also sort of the things that limit the definitions, and that's why we'll talk Bronsted-Lowry, because it's a more general definition. And then Hunter, I'm guessing, did you guys talk about a lot about Lewis acids, bases? We're not going to do that, and Josh as well. We're not going to do Lewis acids, bases in here. We'll reference it very briefly in a couple days, but we're not going to do it here. So guys, again, fundamental definitions, but also too limiting. So the definitions that we're going to use for acids and bases lie here in the Bronsted-Lowry definitions. These are the ones you've got to understand. Yeah. Okay, so guys, compare and contrast, shall we? The Bronsted-Lowry definition of an acid. Ready? It's two words. Proton donor. Done. Oh, you know what? I'm going to need writing tools. So hopefully this still works. There's no guarantees. So guys, it's really this simple. In the Bronsted-Lowry definition of an acid is simply a proton donor. So talk with me about how that's the same and how that is different from the Arrhenius definition. What's the difference? Not water. Guys, the Arrhenius definition is specific to water. The Bronsted-Lowry definition is more general. It does not have to be in water, but guess what? All of the acid-base chemistry that we're going to do in this class is going to be in water, even though it doesn't have to be for it to be Bronsted-Lowry. What's the similarity between the two? H+ ions are the same as protons. Do we need to talk about that? Do you understand why? Hydrogen is made of 1 proton, 0 neutrons, 1 electron. When it becomes an H+ ion, what goes away? The electron. What are you left with? Proton. Good. And then, guys, make the connection. If an acid is donating protons, what will that do to the concentration of protons? It'll go up. So those are the similarities and differences. You okay? Okay. Then, guys, let's do this. Let's talk about the base definition. And the base definition, I'm clicking up here. The base definition, now I'm drawing dots. Can I do this? Look at me. Come back. There we go. All right, guys, the base definition goes like this. A base is a proton acceptor. Guys, now we got to start thinking chemical reactions. Talk to me about the difference between the Bronsted-Lowry and Arrhenius definitions. What's the difference? The water again, right? What's the similarity? Do you see it? So guys, there's a couple different ways that you can come at this. So what we need to do right now is we need to take a deep breath and we need to allow ourselves to become comfortable with something really crazy. You ready? We are talking acid-base chemistry, right? What do acids do? Give away hydrogens. What do bases do? Arrhenius definition. Give away OHs. What happens when those come together? They make water. But now, guys, you've got to understand that all of the chemistry that we are going to do in this unit will always take place in water. So here's a weird way to think about it. When you're an itty-bitty little elementary school kid, where do you play games during school? Well, you go out on the playground and you run around and you play your games and you do your things. But guys, the playground never gets involved in the game, right? It's a surface upon which the game takes place, but the playground is not an active participant in the games that you're playing. This is where that changes. And it's a little bit of a stretch. But guys, you've got to understand, when we do acid-base chemistry, where does that chemistry take place? In water. And guys, water is not a spectator, if you will. Water is an active participant in the games that the acids and bases are playing. So water is not just the environment in which the reactions take place. Water is a participant in the reactions. And that's what makes this stuff a little crazy at times. So guys, here's the thing, and you're going to get good at this. Right now you're clueless, but you're going to get really good at making a decision. And the decision is this: when do we include the water and when do we not include the water? Because you're going to see, guys, for a lot of the chemistry that we're going to lay out in this unit, we are not going to talk about water. The water is there, and the water is the environment in which the reactions are taking place, but we're not going to talk about it. And then all of a sudden, we're going to have to talk about it. And you're going to need to be able to strategically decide, when do we include the water and when do we not include the water. So guys, let's have that conversation revolving around the difference between the definitions. So tell me again what you were thinking there, Caleb. We asked the question, what is the similarity between the base definitions? And go ahead and tell us what you're thinking. Okay, good. Good. Okay, so if you want to look at this, if you want to look at this first, guys, Arrhenius says that bases give away OH. But guys, what do these OHs do? Well, they can accept protons and they can form, I was pushing my luck. I tried to write too fast. Now I'm drawing dots. Hold on. So let's get rid of this. Let's go back here. Let's grab this. But guys, understand, one of the ways of thinking about this is these OHs can grab a hold of protons and they can form water. But guys, there's another way to think about this. Let's think about this idea of proton acceptors. You ready for an example? And I think you're going to want to write this down. You ready? NH3. Ammonia is a base. But wait a minute. How is ammonia a base? Ammonia ain't got any OH. And if ammonia ain't got any OH, how is it a base? Well, guys, look at what happens. Ammonia goes into water. And this is an equilibrium process. It's not a strong base. But guys, I just told you that ammonia is a base. So guys, given the Bronsted-Lowry definition, if ammonia is a base, what's it going to do? Accept a proton. And where does that proton come from? The water. So what does that turn into? NH4 plus. And when that forms NH4 plus, by taking a hydrogen away from the water, what is left over from the water? OH minus, and all of a sudden now we can make this connection because it did in fact increase the concentration of hydroxide. How did it do that? By accepting a proton from water. So guys, and if this seems a little fuzzy to you right now, understand that these kind of things are going to come into very sharp focus as we get deeper into the unit. But guys, the thing that I wanted to make sure you're comfortable with is the idea that sometimes we're going to talk about the water, sometimes we're not going to talk about the water. But in a case like this, we have to, because if we didn't, NH3 wouldn't be a base. So we're going to play with these ideas as we go through this. You guys okay with the chemistry behind it though? Okay, all right. So guys, now that we have a couple working definitions for acids and bases, what we're going to do is we're just going to say this, sort of draw the line in the sand. For this class, we are going to use the Bronsted-Lowry definition to understand acids and bases. You may see the occasional, and let me just help you with this. You may see the occasional multiple choice question on the AP test about what is an Arrhenius acid and base. But guys, all I would do is right next to this, well really if you just wrote down this, you should be fine. The Arrhenius definition is very limiting. That's really the thing they want you to know, is that the Arrhenius definition is very limiting. Okay. So guys, now we're going to transition. You ready? Look at what we just did. We just talked about what happens when bases interact with water. We understand that they can be thought of as either donating hydroxides or accepting hydrogens. However you think about that, we're starting to understand how bases interact with water. What we're going to do now is we're going to talk about how acids interact with water. You don't need to write this down. It's a transitional thought. But here's the idea. Arrhenius definition, what do acids do? Give away hydrogen ions. Bronsted-Lowry, what do? Give away hydrogen ions. Guys, we call them protons, but that definition is the same. This is going to start to feel familiar. You ready? Remember these dudes? Hydronium ions. So guys, this is flat out review from last year, but let's make sure we're clear on this. So guys, the idea is this. When you take an acid and add it to water, and for our purposes, acids only function as acids in the presence of water. When you put these things in water, what do? Well, the hydrogen ions, which are the protons, react with the water to form hydronium ion. Do you remember that? The chemistry looks like this. Hydrogen ion plus water yields hydronium ion. The hydronium ion is actually a trigonal pyramid. It's tetrahedral in domain geometry. It is trigonal pyramid in molecular geometry. But guys, I think we talked about this last year. But if you think about it this way, this is the active ingredient, if you will, in an acid. So if you spill hydrochloric acid on your arm and it's burning you, the hydrochloric acid is not burning you. What's burning you? Hydronium ion. You spill nitric acid on you and it's burning you. No, it's not. It's the hydronium ion. Guys, all acids do is give away protons. Those protons go to water. Those protons form hydronium ion, and that is the reactive part of an acid that you think of as being acidic. So guys, it goes like this. These hydronium ions give these things their characteristic properties, their corrosiveness, their ability to react with metals. All of those things are all the result of hydronium ion. So guys, let's make this personal, if you will. So the idea is this. Instead of just saying H+, let's make this more practical. Let's go HCl. So when we put HCl in water, I think it'll be helpful to think about it this way. What gets formed? Hydronium ion, which is H3O+, and what else? Chloride ion. Make sure it's ion, guys, not Cl. It's Cl ion. So guys, this is the chemistry that takes place when we make hydrochloric acid. Yeah. No, it does not. And that's a good point. It's not a gas. This is aqueous. Remember, on our test, we don't have to write the aqueous because the negative charge tells us that it's dissolved in water. But this is a solvated ion. It is not diatomic chlorine. It's not released as a gas. Yeah. Good question. And the answer, frankly, is yes. That said, they'll tell you in the stem of the free response questions, but we will never do in this class any acid-base chemistry that isn't aqueous. So it'll always be aqueous. What's that? Oh, absolutely, all over. We just don't need to worry about it. So guys, here's the question. This is really the chemistry that takes place in a bottle of hydrochloric acid, right? So if you have a bottle of hydrochloric acid, how much HCl do you have? None. You don't. Guys, there is no HCl in a bottle of HCl. Guys, HCl is a gas. If you had HCl, it would be stored in the same container that we store helium to fill up balloons. Guys, HCl is a molecular gas. It's not a liquid. So in order to make hydrochloric acid, we dissolve the HCl into water. But guys, where does this HCl go? It all goes away. Every single molecule of HCl that you put into a bottle of HCl aqueous reacts with water, forming hydronium ion and chloride ion. So in a bottle of hydrochloric acid, you don't have any HCl molecules. They've all been converted to hydronium ions and chloride ions. Get the idea? Yeah.
So HCl gas is not like corrosive?
Not at all. No, so long as there's no humidity in that container. Yeah, and that's actually, we've had horrible accidents with this with sulfuric acid, because up at Kennecott Copper, they actually, as they're smelting the copper, one of the products is sulfuric acid, H2SO4 gas, and they put it in tanker cars and send it on trains. And if there's any humidity in there, the sulfuric acid molecules react into the water, forming acid and corroding the cars. So long as it's dry, it's a gas and it's non-corrosive. Yeah. Okay. And the reason is because there's no free protons, right? Because the thing that makes an acid corrosive is the hydrogen ions that turn into hydronium. And if there's no water, there's no free protons, and there isn't a corrosive nature to the substance. Yeah. So guys, you okay with the chemistry? Yeah. It has to do with their polarity, right? Yeah, but it is fairly symmetrical, because you've got the symmetrical SO4, which is tetrahedral, and then you got a hydrogen hanging off of each end, and it just isn't polar enough to have strong enough intermolecular forces to keep it. Liquefies very rapidly at fairly high temperatures, but at STP, it's a gas. Yeah, and again, it's because of intermolecular forces. So guys, this is where you then need to get comfortable with the nuances that we talked about a minute ago. So guys, the chemistry that we just wrote up on the board, we can represent one of two ways. So it goes like this. Hydrogen ion that's what acids produce, reacts with water to form hydronium ion. Now guys, at times you are going to find out that we are going to want to represent acids as a source of hydronium ion. But at other times, we don't care about the water and we will simply represent it like this. So when we talk about what acids produce, we can simply say acids produce a concentration of hydrogen ion. So we could just simply do this and say acids like HCl give away hydrogen ion, protons, and then they go and do chemistry. But we could also do this. We can also represent the product of an acid in water as being H3O+. Now guys, this is a really important time for you to focus here and make sure that you understand the answer to this question. Why are those interchangeable? Because the acids are always aqueous, and you can't have one without the other. But guys, what do acids produce? Hydrogen ion. But guys, let's go back to our example. Let's see if we can do this. In our example of HCl, guys, how much hydrogen ion is in a bottle of HCl aqueous acid? How much hydrogen ion is there? None. Guys, every time we put a molecule of HCl into water to form an acidic solution, it gives away one H. Come on. Hold on. Come back. Oh, there we go. Okay. So guys, every time we put a molecule of HCl into water, it gives away an H. But that H does not exist on its own. Where does this hydrogen ion go? To water to form hydronium ion. So guys, the reason that we treat these as being interchangeable is because we are insightful enough to understand that there really is not any hydrogen ion in an acid. The hydrogen ion has all been tied up with water to form hydronium ion, but because this always happens, we can use either one of these, it'll come in, we can use these interchangeably with the understanding that this actually does not exist, and it's actually hydronium ion that exists inside an acidic solution. But because that's always what gets formed, we don't necessarily need to write it. Sometimes it's just simpler to write H+. Do you see what I'm saying? So you may want to make note to yourself and say H+ doesn't exist. This is actually what is formed, but we can still use them interchangeably. So guys, let's call time out. What do you need to talk about here? You okay? Okay. And guys, understand that this interplay between acids and bases and water, this can be a little conceptually challenging at first. This is new. So allow yourself the time to get comfortable with this, because it takes a while, but you'll get there. You guys good? You okay? Okay. So now, guys, we need to continue this baseline conversation about acids and bases. And guys, we now need to talk about conjugates. Now, guys, here's the deal. Last year, we taught you about conjugates, and it was a means to an end. Which one's the conjugate acid? Which one's the conjugate base? You had to figure them out on the homework and the test. Guys, now conjugates are going to become a very important part of our acid-base conversation. We're going to talk about the chemistry of conjugates. So simply being able to identify them is certainly critical, but the conversation is not going to stop there. But that said, let's make sure that you can at least identify them. So guys, it goes like this. When an acid and a base react, and this is all Bronsted-Lowry now. When an acid and a base react, what they do is they form a new acid and a new base. And those are what are termed the conjugate acid and the conjugate base. Now guys, this is where this gets kind of interesting, because even given the little bit of additional knowledge that you have now, you can make sense of what's going on right here. I've tried in the past to try to animate this, and it hasn't worked very well. So we're just going to write it by hand. You ready? Bronsted-Lowry. Guys, do this. Write in a proton with your acid. So guys, talk to me, Bronsted-Lowry. What is an acid going to do with that proton? Give it away. Where's it going to go? To the base. How do you know? Because bases are proton acceptors. So this hydrogen ion is going to go from here to there. But now guys, watch this. What now happened to that acid when it lost the hydrogen? Well, it's missing a hydrogen. And if the acid is now missing a hydrogen, it would like to get the hydrogen back, making it what? A base, but we call it the conjugate base. Now guys, what about the initial base? Well, what happened to this base? Well, this base now has an additional proton. And guys, because the base now has an additional proton that it didn't have before, the base is now proton rich. And now that it's proton rich, what do you suppose it wants to do? Give away the proton, making it what? An acid. Get it? So the thing that lost the proton, the acid, becomes proton deficient. It would like the proton back, making it the conjugate base, and then the base, because it now has an additional proton, would like to get rid of it, making it an acid, which we call the conjugate acid. Do you see the interplay there? So guys, in the Bronsted-Lowry way of thinking, all an acid-base reaction is a transportation of one proton. The proton leaves the acid, goes to the base. That's the end of the chemistry. So let's sort of make sure we're all clear on this. So if you like this better than the arrows that I drew in red, feel free to write it down. And then guys, we are going to share a very, 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 very important point. Do you like the red arrows better, or do you like the words better? Arrows? Some of you are writing down the words, so I'll wait. Go ahead, Carson. And that's what we're about to talk about. Yeah, yeah. If it reaches equilibrium, yeah, that's would certainly be fair. Spencer's saying, could we think of the proton as being the proverbial hot potato? And if it reaches equilibrium, absolutely. Because what would happen is the acid would give the proton to the base, then the conjugate acid would give it to the conjugate base, pushing the reaction in the other direction. So they're just swapping that proton back and forth. But if it goes to completion with the strong acids, no. Okay, and we'll look at that in just a second. So you guys caught up with me here? Okay, so guys, let's do this then. I want to go back up to this reaction, and I'd like to write in a couple real-world examples. So you're going to want these examples. So let's take a look. So let's do this. Let's make our base water. Okay, and if you don't have space around this reaction, feel free to just write this down below. You're just going to have to write it twice. Then guys, let's just stick with what we know. Let's do HCl as our acid. But then guys, down below, let's do this. Here's another acid, CH3COOH, which I think you know to be vinegar. That's vinegar, acetic acid, it's vinegar. Okay, so guys, let's write out the products of these reactions. So what is the HCl going to do? Give away a proton. where's it going to go? To the water. Now, guys, let's be careful. Which one will our conjugate acid be? Let's talk about our products. So join me here. Let's talk about our products. HCl releases a proton. So what's left? Chloride minus. And the hydrogen goes to the H3O, making hydronium plus. So guys, which one of those will be our conjugate acid? Which is the one that now has the proton that could give it away? The hydronium ion. So our conjugate acid will be hydronium ion. And what will our conjugate base be? Chloride ion. Not Cl, chloride ion. Cl minus. Now guys, let's do the same thing down below. We'll talk more about this later, but guys, for now, just understand this hydrogen right here is what we call the acidic hydrogen. It's the one that's given away. So when acetic acid gives away its acidic hydrogen, where does it go? To the water, because that's what acids do. So again, our conjugate acid will be H3O plus. And now what will our conjugate base be? CH3, COO minus, which is the acetate ion. Now guys, check this out because this is really interesting. Let's finish balancing these equations. Well, they're balanced. Let's finish writing them. Guys, notice what we're missing. The arrow. So looking at this top reaction, what arrow do we need? We need this arrow. Do we need an arrow going in the other direction? Why not? It's a strong acid. And guys, you learned way back in chapter 5 that, no, 3? When did we do aqueous chemistry? I think it was 3. Anyway, guys, way back at the beginning of the year, you learned that strong means something. What does strong mean? Goes to completion. So guys, every HCl that you put in gives a hydrogen to water, forms a hydronium, forms a chloride. This goes to completion. It's strong. Now what about this one? It goes to equilibrium. Acetic acid is not one of the 7 strong acids, which you're going to want to go back and review. But guys, these do different things. Go ahead, Eliza. No, this is what we call acetic acid. Vinegar. So when you buy a bottle of vinegar, you're buying a bottle of this in water. So what's actually in vinegar? Well, there's certainly some of this, right? Because this is what happens when the acetic acid goes into water. But there's also some of this, right? Because this reaches equilibrium. What you're going to find out, we're going to do this math in 2 class periods. You're going to find out that it's more than 98% this. It's only about 2% of this that breaks apart. It's very weak. That's why we can drink it and put it on salads. Yeah, okay. So, guys, you okay? Here's the question. Why? Why does the top one go to completion? Why does the bottom one reach equilibrium? And the answer is not because HCl is a strong acid, because HCl doesn't know what it is. HCl hasn't read your chemistry book. HCl doesn't know that it's a strong acid. So guys, what we are now asking is the fundamental question, why is HCl a strong acid and why is acetic acid a weak acid? You ready for the answer? The conjugate base. That's the answer to why is HCl a strong acid and why is acetic acid a weak acid. It's all about the conjugate base. And guys, it goes like this. Chloride is a worthless conjugate base. The book uses the word negligible. Think about that. What does that mean that chloride is a worthless base? What can't chloride do? Steal the proton back from hydronium ion. Chloride cannot get that high. Chloride goes over to hydronium and goes, hey, yo, give me my proton back. And hydronium goes, no way, you're not strong enough to do that. And because chloride can't steal its proton back from hydronium, the reaction does not go the other direction, and it doesn't reach equilibrium, and therefore it makes HCl a strong acid. So guys, what is the answer? Why is HCl a strong acid? Because chloride is a worthless base. Please don't use the word worthless. It's negligible, but worthless makes more sense in my brain. So you ready for this? Why is acetic acid a weak acid? Because acetate ion is not worthless. Guys, acetate ion has the ability to go over to hydronium and say, hey, yo, I want my proton back. And hydronium gives up the proton to acetate ion, driving the equilibrium in both, driving the reaction backwards, therefore reaching equilibrium. So guys, you ready for the big idea? What do you now know about chloride ion, bromide ion, iodide ion, HSO4 ion, nitrate ion, ClO3 ion, and ClO4 ion? They're all worthless bases. How do I know? Because they're the conjugate bases of the strong acids. Do you see how all that fits together? So guys, let's put this in word form. This is very, very important. And it goes like this. The important rule is this. Strong acids and bases form worthless conjugates. And as a matter of fact, the stronger the acid is, the weaker its conjugate base is. And we will quantify that when we start talking about Kw is equal to Ka times Kb, which we'll do in the next unit. Yeah.
So what happens, like, so I know this cool fact that H, then aqueous hydrogen chloride, hydrochloric acid is like, it gives off fumes of HCl. Is it quite dry?
Let's talk about it later. Okay, and then guys, we understand this, that the stronger a base is, the weaker its conjugate acid will be. And Spencer, I do want to talk with you about that, just not now. So guys, now here's what we know. Whether it's an acid or a base, the stronger it is, the weaker its conjugate is. And importantly, the strong acids and bases, and guys remember, strong has a meaning. Strong is not a comparative term. Strong is the term that means completely dissociates. Guys, the idea is that the strong acids and bases have conjugates of negligible strength, which is what causes them to be strong in the first place. You guys okay? Okay, so we're going to cover at least two more things. But let's take a look at this first to make sure that you guys are okay. So conjugates. Let's do this without writing it down. Guys, remember in the Bronsted-Lowry definition, we're just following protons. So does this gain or lose a proton? Well, let's compare. Here's HNO3, there's NO3. What did this do? Lost a proton, so what does that make it? An acid. So what does that make water? A base. So now let's do conjugates. So if this is the acid, what does that make nitrate? Conjugate base. And therefore hydronium is the conjugate acid. And then guys, here's the example of our NH3, right? We talked about this at the very beginning of the day. NH3 attracts a hydrogen from the water, forming hydronium ion and hydroxide ion. So what's the NH3 doing? Acting as a base, accepting a proton that makes water the acid. And then what would that make NH4 plus? conjugate acid because it's now proton rich, and then hydroxide is our conjugate base. Guys, notice too, are these the correct arrows? They are, because HNO3 is a strong acid, so it goes to completion, and ammonia is not a strong base. Let's review quickly. What are our strong bases? Group 1 and heavy group 2 hydroxides, right? So it is not a group 1 or heavy group 2 hydroxide, so it would be weak and it would reach equilibrium. Okay, so guys, what then about water? Here water was our base, here water is our acid. Which one is it? We understand that it's both, and it sounds like you remember we call that amphoteric, right? Which means it can function as an acid or a base, yeah. You know what, Gavin, it's really cool that you thought of that, because guys, so Gavin's question is, what if we've got I don't know if this is exactly how you said it, a weak acid and a strong base, or the other way around? And the answer is this, and we're going to talk about this a lot in chapter 17. The guiding principle is this: if you have a strong of either one, strong acid, weak base, strong base, weak acid, if there is a strong component, it will go to completion. That strong whatever overpowers the weak whatever and forces it to go to completion. Yeah, go ahead. Tons of them, yeah. I think the one that first comes to mind would be the bisulfate ion, HSO4. And well, you don't remember. We actually talked about this in homework in general chemistry, but I'm sure you don't remember. This can either take in a hydrogen and function as a base, or release its additional proton and function as an acid. How do you know what it'll do? We'll actually quantify that in chapter 17. Yeah, but yeah, there's tons of stuff that are amphoteric. Okay, so guys, you okay with this idea of amphoterism, acid or base? Because this is about to get interesting. You okay with the idea? So which one is water? Is it an acid or is it a base? Yeah, but guess what? Not only, oh, hold on, let's actually jump. Oh, these slides are out of order. Here, hold on a second. I'm going to just reorder these. These got out of order. So guys, not only is water an acid or a base, but because it's amphoteric, it actually has the ability to ionize itself. You want to write this down. So guys, imagine that you've got a big old thing of water. So you've got all these water molecules in there. But when water gets around other water molecules, just by the law of averages, we know there are going to be collisions, and we know water has a hydrogen that it can give away and function as an acid, but we also know that water has the ability to take in a hydrogen and function as a base. And guys, it actually does that. So write the balanced equation for it. Write the balanced equation for water reacting with water. What does it look like when water reacts with water? Just a second. Would you agree it's this? Did you all draw the double-headed arrow because it's certainly not strong? Yeah? Then do this. Write the Kc expression for this. You guys are about to have an aha moment, and we'll stop with it. So let's see if you learned anything at the end of the last unit. Kc is equal to products divided by, products divided by reactants. And guys, are you okay with me just doing that because there's two of them? Okay? You good? Okay, and you all wrote this down? You're all good? Because you're all wrong. If you wrote this down, you're wrong. Why? Say it again. Guys, this is a heterogeneous equilibria. Let's put some subscripts on here. Liquid, liquid, aqueous, aqueous. And what do we remember about heterogeneous equilibria? Heterogeneous equilibria, we do not include, which ones? The liquids or the solids, because they do not have molarities and they do not have pressures. So this is gone. And when we remove that, we now have the equilibrium expression that works only for what substance? Water. So we replace the C with a W. Find it on your equation sheet. You see it? There it is. Kw is equal to hydrogen ion concentration times hydroxide ion concentration. And then you'll notice they give you the value for Kw, which is 1 times 10 to the negative 14th. Notice no units. Kc, Kw is a dimensionless number. But guys, it then looks like, this is still in the way. Sorry, just a second. I'm just going to get this completely out of the way. There we go. So guys, it then looks like this, right? So you guys ready to have a big old aha moment? So guys, and you see this on your equation sheet. They did the chemistry. They measured, they figured out, they did this in lab, and they figured out the value for Kw. 1 times 10 to the negative 14th. Do you see it? Are any of you making the connection? What is it? It's the pH scale. Because guys, look. If this is 1 times 10 to the negative 14th, what do you know about the concentration of those? What do they have to be? The same, right? Because where did this come from? From a water forming this, right? And for every one of these that gets formed, what about this? One of those is formed. So these have got to be the same, which means we can call it x, and they're the same, so it's x squared. So what then is the square root of 10 to the negative 14th? 10 to the negative 7th. And then guys, from last year, you might remember that pH is equal to the negative log of hydronium ion concentration, which is equal to the negative log of 1 times 10 to the negative 7th, which is equal to 7. That is why pure water has a pH of 7. It is because the hydronium ion concentration is 10 to the negative 7th molar, which then leads us to the value of Kw, which is 10 to the negative 14th. Guys, that is the very foundation of the pH scale, because pH is the concentration of hydronium ion, and in this case for pure water it's the same as hydroxide, and that's where we get pH 7 for pure water. You get the idea? Kind of groovy. Now guys, here's the thing that's really interesting about this, and this is where we're going to wrap up the day. This expression up here at the top of the board not only holds true for pure water, but it also holds true for any aqueous system, whether it's an acid or a base. So guys, the bottom line is this. This don't change, right? We understand that about K values. K doesn't change so long as we don't change what? Temperature. Guys, if we don't mess around with the temperature, K doesn't change. Whether it's KW, KC, whatever you want to call it, it don't change. So guys, if K doesn't change, check this out. If we have a vat of pure water, and if we dump hydrochloric acid into it, what happens to this? It goes up. Why does it go up? Because the hydrochloric acid gives away protons. Where do the protons go? To the water, forming a hydronium ion. But guys, the trick is this. If this goes up, what has to happen to hydroxide concentration to keep this from moving? It's got to go down proportionally. That's the thing that's cool. And guys, the way that I think about this is I think about this as if it were a seesaw. And you don't need to write this down, but mentally that's the way I picture it. That you can picture KW as being your fixed point as if it is like a fulcrum on a seesaw. So the idea is if this is our fixed point, then this becomes the fulcrum on our seesaw, and if this goes up, this has got to go down proportionally to keep this from changing. And so guys, what that means is that if we know the concentration of hydronium ion, we can figure out the concentration of hydroxide ion, because this is always 1 times 10 to the negative 14th. You get the idea? And so guys, then the question becomes this. How do we get the concentration of hydronium ion? That's pH. And we'll just write this down, and this is where we're going to stop. pH is, and I already wrote it down earlier, the negative log of the hydronium ion concentration. So guys, this is where we're going to stop, but let me show you where we're going. What we now need to talk about is how do we know the hydronium ion concentration? How do we know H3O concentration? The answer is pH. That's where we're going next. We are going to pick up on Wednesday by talking about pH. So guys, with that said, here's your homework. Let me just tell you right now, guys, and I wonder, well, I guess I don't care if you agree really. I think some of you were surprised at how relatively light the homework load has been in this class, given that it's a college course. I don't know if you've had that experience, but typically year after year, I have people go, I thought it was going to be more. I mean, is it ever more than an hour? No, it's going to be. Guys, expect, not always, and again, you know me well enough to know I would never waste your time. I respect you guys too much to do that. I will never give you busy work. But this requires a lot of work. So this assignment's pretty big. We will grade, well, let's say this differently. Do what of this you can. It covers the entire day's stuff, which is going to continue into Wednesday as we talk about pH and things like that. But guys, do what of this you can. We will pick up on Wednesday and finish up this day, and then maybe even get into the next day's stuff. But we will grade this before we go on. Yeah. Yeah, good. Thank you. Let's talk about it. Guys, if you look on page 12, Carson is noticing that it doesn't give you the same equation, does it? If you look at the KW expression, it gives you hydrogen and hydroxide, not hydronium and hydroxide, which guys is a great example of what I was trying to share with you earlier, which is this, guys. We can use either one. Because H plus and H3O plus for an acid are the same. Because we understand that in an acid there really isn't any H plus. It all goes to hydronium, so it's a great example of where we can use either definitions. It's easier. Because we understand, because we're not slaves to this table, we understand there is no hydrogen ion, that it's actually hydronium, and it's just easier to represent it this way. Again, what you're going to find is as we get deeper into this unit, it becomes very clarifying to not include the water. So guys, we have about 3 or 4 minutes left. We will see you on Wednesday. For those of you that did not take the test, I will plan on you Wednesday after school. Nate, thank you. It's dried out nicely. And guys, we'll go when the bell rings.